Welcome to the fifth lecture on refrigeration and air conditioning. This is a continuation of last lecture wherein we have reviewed some of the fundamentals of thermodynamics, and the specific objectives of this particular lesson are to introduce methods for evaluating thermodynamic properties, introduce TS and pH diagrams, and analyze some important thermodynamic processes and derive expressions for heat and work transfer in these processes. And at the end of the lesson, you should be able to evaluate thermodynamic properties using equations of state, tables and charts, identify various regimes on TS and pH diagrams, and estimate heat and work transferred in various thermodynamic processes. Now let us look at thermodynamic property evaluation. In order to carry out calculations in refrigeration or in any thermodynamic calculations on processes or cycles, we need to know several properties. Some of the properties can be measured directly. For example, properties like pressure, temperature, volume, specific heat can be measured directly, whereas some of the properties such as internal energy, enthalpy, entropy cannot be measured directly. So thermodynamic relations have been developed to measure properties which cannot be measured directly in terms of properties that can be measured using carrying out some experiments. Let's look at thermodynamic relations. These are the what I am going to show here are the fundamental relations which are obtained using first and second laws of thermodynamics. And the first relation is given by TdS is equal to du plus PdV. This is known as first TdS equation, and second TdS equation is given by TdS is equal to dH minus VdP. And these two relations are very important, and we shall see how we use them. And since these equations contain only properties, they are valid for both reversible as well as irreversible processes. And two more thermodynamic relations can be obtained by defining two new properties known as Helmholtz function and Gibbs function. Now let's look at various methods used for evaluating thermodynamic properties. The methods used are thermodynamic equations of state, thermodynamic property tables, thermodynamic property charts, direct experimental measurements, and formulae of statistical thermodynamics. Now let us look at the first method, what is known as thermodynamic equations of state. They are also known as EOS. And a typical EOS relates absolute pressure P, temperature and specific volume. One of the simplest examples of an EOS is that the specific volume of a solid is a constant. So this is one of the simplest possible equations of state. Next simple equation of state is that for an ideal gas, that is given here, and as you know very well, for an ideal gas the relationship PV is equal to RT holds good, where P is the absolute pressure, V is the specific volume, R is the gas constant, T is absolute temperature, and the gas constant R, as you know, is given by the universal gas constant divided by the molecular mass. And let me just repeat what is an ideal gas. I am sure all of you know that a gas is said to be an ideal gas if the intermolecular forces are negligible, and also the volume occupied by the gas molecules is negligible compared to the system volumes. Under these two assumptions, we can call a gas as an ideal gas. And under what are the conditions under which a real gas behaves as an ideal gas, that is given here. A real gas can be approximated as an ideal gas if it has a low molecular mass and its temperature is relatively high and its pressure is low. That means for a relatively low molecular mass, gases at high temperatures and low pressures can be approximated as ideal gases. And for these ideal gases, as you know, we can use the ideal gas equation. So ideal gas equation is one of the simplest possible equations of state. Now let us look at how to evaluate the enthalpy change, entropy change, internal energy change for an ideal gas. So these equations are given here for internal energy change, specific internal energy change, specific enthalpy change, and specific entropy change of an ideal gas. The first equation, U2 minus U1, gives the specific internal energy change, and it's given by CV into T2 minus T1, where CV is an average specific heat at constant volume, and it's an average value between T1 and T2. And the next equation is H2 minus H1, that is nothing but specific enthalpy change is equal to Cp into T2 minus T1, where Cp is the specific heat at constant pressure, and it's assumed that it is either constant or we are taking an average value for the interval T1 to T2. Next, using the first TDS equation, we can find out what is the entropy change of an ideal gas, that is given by S2 minus S1 is equal to CV on ln T2 by T1 plus R ln V2 by V1. This is obtained using first TDS equation, and then using the second TDS equation we can also find out entropy change in terms of Cp and pressures, that is given by S2 minus S1 is equal to Cp ln T2 by T1 minus R ln P2 by P1. And as you know very well, the difference between Cp minus Cv is equal to gas constant. And one thing is I am sure that you remember that for an ideal gas the internal energy and enthalpy are functions of temperature only, and from the equations you can see that the internal energy change is given by Cv into delta T, and for ideal gases Cv is only a function of temperature. So overall the internal energy change is only a function of temperature. Similarly, the enthalpy change is also a function of temperature only. Now let us look at real gases. Ideal gas equation cannot be applied for gases with complex molecular structure, and you cannot apply the ideal gas assumption also when the gases are at high pressure and low temperatures, and when the gases approach the saturated vapor region. That means under these conditions, if you are applying ideal gas equation, it will result in significant errors. Then how do we handle these situations? For these situations we have slightly more complex equations of state, which are even the more complex are more accurate. Let us look at some of these equations of state, typical equations of state. The first one, as you know, is what is known as van der Waals equation, and it is given by P plus A by V square into V minus B is equal to RT. So if you compare this equation with the ideal gas equation, you find two differences. Instead of P, we have added a term A by V square to the pressure, and this term A by V square accounts for the intermolecular forces between the molecules. And the second difference is the term B. Instead of writing V, we have written it as V minus B, and this B accounts for the volume occupied by the gas molecules. So A by V square term accounts for the intermolecular forces, and the term B accounts for the volume occupied by the gas molecules. And it can be shown that for a particular gas the constants A and B are related to the critical properties. That means you can express A and B in terms of the critical temperature, critical pressure and critical volume. And the next equation of state is what is known as Redlich-Kwong equation. This is again, if you compare, this is slightly different from van der Waals equation. Again you have here P is RT divided by V minus B minus A divided by square root of T into V plus B. Again you have the form is slightly different, and we have introduced two new constants A and B, and similar to van der Waals equation, these constants A and B are functions of the critical point and also the nature of the gas. Similar to this, we can have many more equations of state. People have developed many more equations of state which are suitable for certain conditions and for certain working fluids, etc. For example, we have what is known as a RKS equation, which is a modified Redlich-Kwong equation. Similarly, we have another very popular equation known as Martin-Hove equation. So these equations we will be discussing again when we discuss refrigerant property evaluations. Let us look at one general equation, what is known as virial equation. This virial equation is given by PV is equal to RT plus A by V plus B by V square plus C by V cube plus etc. I mean that means you can go on adding terms, and these constants A, B, C are known as virial coefficients, and they are functions of temperature only, and they have to be evaluated using experimental data. So this is one form of what is known as a virial equation, and as you can see, if A and B and C become 0, then this virial equation boils down to a simple ideal gas equation of state. So this equation is very useful, and the equation of states along with thermodynamic relations are used to obtain relations for properties that cannot be measured directly in terms of properties which can be measured directly. I am sure that you have studied this in your basic thermodynamics courses, and for more details you can refer to any standard thermodynamics book. Now let us look at properties of pure substances. How do we define a pure substance? A pure substance is one whose chemical composition does not change during thermodynamic processes. That means it does not undergo any chemical reactions as it undergoes the thermodynamic process. Such a substance is known as a pure substance. What are the examples of a pure substance? The common examples are water and pure refrigerants. And water and pure refrigerants are very, very important in refrigeration and air conditioning, and we will be dealing with these things very frequently again and again. Now let us look at the property evaluation of pure substances. The properties of pure substances can be shown conveniently on pH and TS diagrams. Let me show a typical pH diagram. This figure here shows a pH diagram. So here you have a solid region and a liquid region and a gaseous region, and you also have interfaces. For example, this is the region in which solid and liquid exist in equilibrium. This is the region in which liquid and gas exist in equilibrium, and this is the region in which solid and gas exist in equilibrium. So this is a typical phase diagram of a pure substance on pH coordinates. That means we have H on the x-axis and P on the y-axis, and these lines show the isotherms. That means constant temperature lines, and the temperature increases in this direction. That means this temperature is greater than this temperature, and you can see that in the liquid region the enthalpy of the constant temperature line is almost vertical, and it remains horizontal in the liquid plus gas region. That means in the two-phase region the constant temperature line is horizontal. Of course, this is in accordance with Gibbs phase rule, and when a pure substance boils or condenses at a constant pressure, its temperature remains constant. That is the reason why it is horizontal here. Again, in the two-phase region you can see that when the pressure is reduced, the constant temperature lines become almost vertical. That means under these conditions they begin to behave as ideal gases. That is why they will become vertical. And here there are two important points. One is what is known as a critical point. As you know, critical point is the point where the saturated liquid line, that means this line, and the saturated vapor line, these two lines join. So critical point is the point at which the saturated liquid line and saturated vapor line join. This is very, very important, and we shall see later how this influences the selection of refrigerants. And physically, when the working fluids exist below critical point, you can distinguish liquid and gas. That means if you have collected this liquid and gas mixture in a let's say a glass beaker, then a meniscus forms between the liquid and gas phases. Whereas if the working fluid is above the critical point, you cannot make any distinction between liquid and gas, and that region is known as a supercritical region. So there is another important point known as triple point. So as you know, probably the triple point is a point at which all the three phases, that means solid, liquid and gas, exist in equilibrium. So that point is shown here. So this is the typical pH diagram for a pure substance. Now let us look at a typical TS diagram, phase diagram on TS coordinates. So again, this diagram shows a phase diagram on TS coordinates. So you have entropy on the, I'm sorry, it has gone back. You have the entropy on the x-axis and temperature on the y-axis. Again, you can see the solid region, gaseous region, and liquid region. And you can also see the liquid, solid plus liquid two-phase region, and liquid plus gas region, and solid plus gas region. And you can also see the saturated liquid line and saturated vapor line, and the critical point and the triple point. The saturation temperature of a pure substance is a function of pressure only. So what do you mean by saturation temperature? Saturation temperature, for example, for a liquid vapor mixer can be defined as a temperature at which the liquid and gaseous phases exist in equilibrium. That means at a given pressure, the temperature at which the liquid and gas phases exist in equilibrium is known as a saturation temperature for the liquid gas phases. Similarly, you can also have saturation temperature for solid liquid or solid gas regions. and the relationship between saturation temperature and pressure is given by an important relation known as Clapeyron relation. The Clapeyron equation represents the dependence of saturation pressure on saturation temperature, and that equation is given here. This is the equation where dP by dt is nothing but saturated vapor curve, a variation of saturation pressure with temperature, and it can be shown that this is equal to latent entropy of vaporization divided by the difference between the specific volume of the gas and vapor. VFG as it is shown here, nothing but the difference in the specific volume of the gas and the fluid. G stands here for saturated vapor and F stands for saturated liquid. So dP sat by dt is given by SFG by VFG, where SFG is the difference between the entropy of the saturated vapor and the entropy of the saturated liquid, and VFG is the difference between the entropy of the saturated specific volume of the saturated vapor and the specific volume of the saturated liquid, and this can be shown to be equal to HFG divided by Vg minus Vf into T. This equation is derived because for the two-phase reason, the entropy of vaporization is nothing but enthalpy of vaporization divided by the temperature, and as you know, for a pure fluid the temperature remains constant, so SFG is nothing but HFG divided by T. So we can write this equation in terms of these equations. Even though this equation looks quite simple, it's very useful because it relates properties which cannot be measured directly in terms of properties which can be measured directly. And the simplification of Clapeyron equation results in, if you are assuming ideal gas behavior, and if you also assume that the specific volume of the saturated liquid is much smaller than the specific volume of the saturated vapor, and the latent heat of vaporization does not vary much with temperature. If you are making these assumptions, you can show that this is nothing but since Vf is negligible compared to Vg, you can drop this term. So this becomes HFG by Vg into T, and T can be written as Vt can be written as P by RT. So using the ideal gas equation and these assumptions, ultimately you arrive at this relation. That means dP sat by dt is equal to P sat into HFG by RT square. Now you can integrate this equation between two states, 1 and 2, and if I am taking a state 1 as a reference state, that means pressure is 1 atmosphere and temperature is normal boiling point, that is my reference state 1, and the state 2 is any arbitrary temperature at which I would like to find out the saturation temperature. That means I am integrating the Clapeyron equation between a reference state of 1 atmosphere pressure and normal boiling point and any arbitrary state T. So you get this equation, and using this equation, this is a very useful equation. You can see that normally normal boiling point can be obtained, and this is the temperature at which you want to find out the saturation pressure. So this is known to you, and this will be generally known, and this can be measured or this will be known. So you can find out using this relation what is the saturation pressure at any temperature T. So this is the usefulness of Clapeyron equation, and this equation also tells you that if you are plotting ln P sat versus 1 by T, you get a straight line, and the slope of which will give you the latent heat of latent heat of vaporization divided by the gas constant. And one thing you must remember here is, here the pressure is expressed in terms of atmosphere, and temperature T should be in absolute, that means in Kelvin, degrees Kelvin. So for pure substances, just now as I said, the saturation temperature is only a function of pressure, and the saturation temperature at 1 atmosphere is called as normal boiling point, or NBP. You know this very well. Now the definition of normal boiling point. Now let us look at typical normal boiling points of some refrigerants. So what is given here is the fluid and its normal boiling point. For example, for the refrigerant R11, the chemical formula is CCl3F, and it has a normal boiling point of 23.8 degrees centigrade. And R12, which as you know is a very popular refrigerant, and its chemical formula is CCl2F2, and it has a normal boiling point of minus 29.8. Similarly, R22 has a normal boiling point of minus 40.8. R134A has a normal boiling point of minus 26.5. Likewise, you can find out the normal boiling points of various refrigerants, and this data is very much available in literature. Now, for pure substances, this is one peculiarity: the boiling point and dew points coincide. Similarly, the freezing point and melting point also coincide. That means, if you are boiling, if you are keeping the pressure constant, and if you are boiling a liquid, then the temperature at which you find the first droplet of is some temperature T, and now you come in the reverse direction. That means you have a vapor and you are cooling it isobarically at the same pressure, and the temperature at which you find the first droplet of liquid, that is what is known as dew point temperature, and the temperature at which you find the first vapor bubble is known as the boiling point. And for the pure fluids, the boiling point and dew points coincide. Similarly, the freezing point and melting points coincide. For example, at 1 atmospheric pressure, the boiling point of water is 100 degrees centigrade. Similarly, the dew point of water is also 100 degrees centigrade. Why I am stressing this is for mixer, that means a mixer of two refrigerants, the boiling point and dew point may not coincide. Similarly, the freezing point and melting point may not coincide. Okay. Now, this is the repetition of whatever I have stated earlier. The critical point, the definition of critical point, it is the point at which the saturated liquid and saturated vapor lines merge, and the triple point is the point at which the solid, liquid and vapor phases coexist in equilibrium. Let me give some typical values of critical point and triple point for water. For example, for water, the triple point is 0.1 degree centigrade, and the pressure at triple point is 0.006112 bar, and its critical point is at 374.2 degree centigrade, and the pressure at critical point is 221.2 bar. And for carbon dioxide or for dry ice, the triple point is minus 56.6 degrees centigrade, and the pressure at triple point is 5.18 bar, and the critical point is 31 degrees centigrade and 73.8 bar. As I mentioned earlier, all these things are very, very important, and they play a major role while selecting suitable refrigerants for a given application. So, we will be discussing the importance of triple point, critical point, etc. when we discuss selection of refrigerants. Now, in most of the refrigeration applications, we really won't be dealing with the solid phase. That means we won't be dealing with solid and liquid phases or solid and gaseous phases. Of course, there are some applications. For example, if you are using ice for a refrigeration purpose, then obviously you will be dealing with solid liquid equilibria. Similarly, if you are using, let us say, dry ice, then you will be dealing with solid gas equilibria. But in most of the thermodynamic cycles which we are mostly interested in, we will be dealing with liquid gas interface. So, we will be concentrating most of the time on phase diagrams for liquid gas phases. So, let us look at TS and PS diagrams for liquid vapor regimes. There, as I said, they are very useful in refrigeration calculations. So, let me show a typical TS diagram. So, here we have entropy S on the x axis and temperature T on the y axis, and this is a typical curve, and this is your saturated liquid curve, and this is your saturated vapor curve, and this is the point at which both of them join, that is known as your critical point. And on this diagram you have this subcooled liquid region, and this is superheated gas region, and this is liquid plus gas two phase region. That means you have a single phase region here, two phase region here, and again a single phase region here. And on this figure I have shown two isobars, that means two constant pressure lines, P1 and P2. So, you can see the shape of the constant pressure lines. It has slopes in the single phase regions, whereas it becomes horizontal in the two phase region. This is again in accordance with your Gibbs phase rule, or based on the fact that when a liquid boils at a constant temperature, pressure also remains constant. That is the reason why you have a horizontal isobaric line in two-phase region. And here the pressure P1 is greater than P2, that means pressure increases in this direction. And let us look at one isobar 1, 2, 3, 4, and here the region 1 to 2, that means this region. This region is in the subcooled condition, and this region is in the two-phase zone, and this region is in the single phase superheated condition. One thing I would like to point out here is that normally the data for the subcooled liquid region is generally not available. We have the data for this region and data for this region. So most of the times we do not have the data for subcooled regions, and subcooled data is also required for refrigeration calculations. In such cases we make certain assumptions and certain idealizations. Here, as I mentioned, this line is a constant pressure line, and this line is a saturated liquid line. Even though they seem to be distinct here, in actual case they are very close to each other. So one approximation we can make is they almost merge. That means the isobaric line coincides with the saturated liquid line. So that is one of the assumptions. It's a very useful assumption. And another assumption is that, and it can be shown using your thermodynamic relations, that if you want, let us say, the properties at this point A, which is in subcooled region, so they can be approximated with saturated liquid properties at point A dash. Okay, this is one very useful assumption, and most of the time we will be using this assumption. That means if you want, let us say, a liquid exists in subcooled condition, and let's say that its temperature is 30 degrees centigrade and it is at some pressure, and it is at subcooled condition. So we would like to find out what is the internal energy and enthalpy at these conditions. So what we can do is, instead of finding the subcooled conditions, we can assume them to be equal to the saturated liquid properties at 30 degrees centigrade. So this is one very useful idealization, and we will discuss this when we do or perform refrigeration calculations. Now, similar to TS diagram, we can also have PS diagram. This figure shows the PS diagram here, and these are the isobaric lines. Since you have pressure on the y-axis, obviously isobaric lines become horizontal and pressure increases in this direction, and on x-axis you have enthalpy. And I have not shown here, but the isothermal line, that means constant temperature lines, will be typically something like this. Okay, that means again they will be horizontal in the two-phase region, and they become sloped in the single phase superheated region, and they become almost vertical in the low pressure zone. And here again I have shown the process for the pressure P1, the process 1, 2, 3, 4, where 1, 2 is in the subcooled liquid region, process 2, 3 is in the two-phase region, and process 3, 4 in the superheated region. And again you can see that as I have mentioned, the properties at this point A can be approximated, and they can be taken as equal to the saturated liquid properties at this condition. Okay, and this pH diagram and TS diagrams are very useful for performing refrigeration calculations, and we shall see most of the times we will be showing the cycle diagrams on the TS and PS diagrams. So one use of these TS and PS diagrams is that you can find out the required properties using these charts or diagrams. And second use of these charts is you can also represent the thermodynamic cycles on these charts, so that you can directly perform various calculations using these charts. Okay. So as I mentioned, and from your from the last class, using the second law of thermodynamics and from TDS relations, it can be shown that for a reversible process 1, 2, let us say that a reversible process 1, 2, the area under the curve 1, 2 in TS diagram is equal to the heat transfer during the process. This is from your Clausius inequality, where entropy change in a reversible process is given by the heat transfer rate in the during that process divided by the temperature at the boundary. So using that statement, we can easily show that the area under any curve 1, 2 on TS coordinates or on TS diagram is nothing but the heat transfer during the process. So if you can plot the process on the TS diagram, and if you can measure what is the area under the curve 1, 2, then you have the heat transfer during the process. This is very, very useful. And for all practical purposes, as I mentioned just now, the enthalpy of split may be taken as equal to the enthalpy of saturated liquid at the subcooled temperature. Now let us look at saturation properties of pure fluids. What do we mean by saturation properties? Let us say that again I would like to repeat here that most of the times we will be dealing with liquid gas either in the single phase or two phase or in superheated regions. So how do we evaluate the properties of liquid gas mixers in two phase regions? So the equations shown here are for finding out the two phase properties. That means liquid gas equilibrium properties. For example, this equation gives the specific volume of a two phase mixer in terms of saturated liquid specific volume, saturated liquid specific volume and saturated vapor specific volume, and X here is nothing but your dryness fraction or quality. I am sure that you have used these correlations, or you have used these relations while performing calculations in basic thermodynamics. Similarly, you can express the specific internal energy U of a two phase mixer in terms of the dryness fraction X and the saturated liquid internal energy and saturated saturated vapor internal energy. Similarly, the properties of enthalpy and entropy of the two phase mixer can be expressed in terms of saturated property and the quality. That means if you want to find out the mixer properties, you need to know what are the saturated properties first, and you also need to know what is the dryness fraction or quality. And you probably remember that the quality or dryness fraction is defined as the mass of the vapor in the mixer divided by the total mass of the mixer. So that is the definition of dryness fraction. Now let us look at the second method for evaluating thermodynamic properties. We have seen thermodynamic equations of state and some thermodynamic diagrams or thermodynamic property charts. So now let us look at thermodynamic property tables. Normally the property tables are available for saturated region, that means for the two phase region and also for the superheated region. And the saturated and superheated property tables for steam are used for calculating power plant calculations, and I am sure that you must have used them in your basic thermodynamics. And the internal energy, enthalpy and entropy values reported are based on a reference state which may vary from table to table. This is a very important point. That means when you are using a thermodynamic property table, as I mentioned earlier, you do not have any absolute values for internal energy or enthalpy or for that matter entropy, provided you are not using the third law of thermodynamics. So normally the internal energy, enthalpy and entropy values are values with reference to a particular datum state. That means all tables, they first define a reference state, and at that reference state they give arbitrary values for internal energy, enthalpy and entropy, and the internal energy, enthalpy and entropy at any other state are given with reference to the reference state. So basically what the value of enthalpy, for example enthalpy of H that you see in a table is nothing but H minus H corresponding to the reference state. Okay, similarly for the internal energy and entropy. So as long as you are using the same table, then it doesn't make any difference, and what reference values are chosen do not come into picture, because normally we will be dealing with enthalpy changes, entropy changes, internal entropy changes, internal energy changes, etc. So the reference state doesn't come into picture. So you are safe as long as you are using the same thermodynamic property table. But if you are using tables from different sources, then you have to know what are the reference states. You must make sure that the reference states are not different. If they are different, then you have to make suitable corrections and then only use the enthalpy and entropy properties. Normally the saturation property tables are either temperature or pressure based. For example, a saturated temperature based property table, they give temperature as an independent variable, and they give all other properties as functions of temperature. That means you have for example, let us say take water, they say the typical table for water looks like this. Let us say the temperature of water is at 10 degrees centigrade, then the table gives you, the saturated table gives you what is the saturation pressure at 10 degrees centigrade. Then it also gives you what is the saturated liquid properties at 10 degrees centigrade and what is the saturated vapor properties at 10 degrees centigrade. So this is a typical table based on temperatures. Similarly, you can have saturation table based on pressure. That means the pressure is the independent variable. Let us say that 1 bar pressure, then at 1 bar pressure they give what is the saturation temperature and what are the saturated liquid and vapor properties. So you can have either saturated either temperature based saturation tables or pressure based saturation tables. And normally the superheated tables are available for different pressures and degrees of superheat. We shall discuss these tables when we actually perform the refrigerant calculations. And if you look at any of the textbooks on thermodynamics or refrigeration, at the end of the textbooks all these property tables are available for a wide variety of refrigerants. And I am sure that you must have used these tables in your basic thermodynamics. Okay. Now let us look at some common thermodynamic processes. In refrigeration and air conditioning, we come across a wide variety of processes, and if you want to find out what is the performance of a particular process or a performance of a particular cycle, we need to know or we need to understand that particular process, and we have to estimate what is the heat transfer during that particular process, or what is the mass transfer during that particular process, what is the entropy transfer during that particular process. All these terms are required in order to evaluate the performance. So let us look at some of the very basic processes. I will give the basic process and a typical example and the suitable equations for work transfer, heat transfer, energy transfer or energy change, etc. Okay. So the first process, a simple process, is a constant volume or isochoric process. So isochoric process means the volume does not change, and a typical example is the heating and cooling of a gas stored in a rigid vessel. So that means we have a rigid vessel, and it consists of a gas, and which is the system here, and we are heating the gas. And this process, this example is typically a non-flow process. That means neither the gas is leaving nor entering into the rigid vessel. For this kind of a system, if you are heating or cooling the gas, what are the typical equations for work transfer, heat transfer and entropy change? So those equations are given here. How did we get these equations? For example, this equation, how did we get this? For a non-flow process, if you remember, the work transfer 1W2 is given by integral PdV integrated between 1 to 2, and here dV is the volume change. Since it is a rigid vessel, dV is equal to 0. So work transfer rate is equal to 0. So that's how you get this equation. So the work transferred in a simple heating and cooling of a gas stored in rigid vessel is 0, provided we do not have any other modes of work transfer. For example, you don't have any electrical heater or any other magnetic or chemical modes of work transfer. Okay. Then we can find out this expression for heat transfer rate during this process using the first law of thermodynamic process, first law of thermodynamics for a non-flow process. As you know, first law of thermodynamics for a non-flow process is given by 1Q2 is nothing but 1W2 plus integral du. Since 1W2 is 0, you simply have here 1Q2 is equal to integral du. Since this is the property, the integral du can be written as U2 minus U1, where U2 is the total internal energy at state 2 and U1 is the total internal energy at state 1. Of course, this is based on the assumption that other changes like kinetic and potential energy changes are negligible. And this equation can also be written in terms of the first TDS equation. If you remember, the first TDS equation is given by TDS is du plus PdV, okay, and PdV is 0 because there is no volume change. So TdS is simply equal to du. So ds is du by t. So if you are integrating this between state 1 and 2, you get that S2 minus S1 is nothing but mCv into ln T2 by T1. Okay. You can also think of other non-flow processes. For example, another very simple example of a constant volume process is that of a heating or cooling of a solid. For example, when you are heating or cooling a solid over a temperature difference which is not too large, then its volume remains constant, and the heat transfer rate during that process is simply equal to mc into delta T, and for a solid specific heat at constant volume and constant pressure will be same. So it's simply mCp into delta T, and the entropy change S2 minus S1 is nothing but mc ln T2 by T1. Okay. Now let us look at another simple process that's known as constant pressure or isobaric process. So the iso here stands for a constant. That means whenever we say iso something, that means some property is remaining constant. So in a isobaric process, the pressure remains constant. And here let us take the example of again a non-flow process. We are heating or cooling a gas which is contained in a piston cylinder assembly, and let us say that the piston is not spring loaded or anything. That means it is acting against a constant external force. If that is the case, the pressure remains constant. That means the pressure exerted by the piston remains constant. And if you assume that the piston is frictionless, that means the movement takes place without any friction, then we can have an ideal isobaric process. And for this isobaric process, the equations are like this. For example, this first equation is nothing but first law of thermodynamics for an isobaric process in a non-flow process. Okay. And as you know very well, this is nothing but the statement of first law. Okay, 1q2 is nothing but u2 minus u1 plus 1w2. And how do we find 1w2? 1w2 for a non-flow process is the integral pdv, and if you assume that this process is quasi-static, then you can perform the integration, and since pressure is constant, this is simply equal to p into v2 minus v1, where v2 is the final pressure and v1 is the initial pressure. So work done during a constant flow process is nothing but P into delta V or P into V2 minus V1. And the heat transfer rate can also be written in terms of enthalpy difference. For example, if you are substituting this here, and if you are using the definition of enthalpy, H is U plus PV and P is constant here, you can get this equation. Okay, that means you can write 1Q2 as m into H2 minus H1, where m is the mass of the system and H2 is the specific enthalpy at the final state, and H1 is the specific enthalpy at the initial state. And H2 minus H1 can be written in terms of specific heat at constant pressure and temperature difference. That means 1Q2 is mCp into delta T or mCp into T2 minus T1. And using the second TdS equation, you can obtain this relationship for change in entropy. Okay, if you remember, second TdS equation is given as TdS is dH minus VdP. So VdP is 0 because pressure is remaining constant. So ds is integral dH by T, and if you are performing the integration between state 1 to 2, you get the expression for entropy change during an isobaric process. Okay. So let us look at another process. This is known as a constant temperature or isothermal process. A typical example of this is compression expansion of a gas with heat transfer. That means again we are taking a non-flow process. A gas is undergoing compression or expansion in a piston cylinder assembly, and at the same time the heat transfer is taking place between the system and surroundings. The heat transfer is taking place in such a way that the temperature of the system remains constant. So this is then the process becomes an isothermal non-flow process. And for this process, the governing equations for energy, for work transfer and heat transfer and energy entropy transfer are given here. Okay. For example, this equation is nothing but your first law of thermodynamics for a non-flow process, a general first law of thermodynamics for a non-flow process. And since you have volume change here and pressure also can change, the work done during this process has to be obtained by integrating this process 1 to 2, and so you must know the relationship between P and V in order to perform this integration, and in order to find out the work done. Of course, the process has got to be quasi-static, otherwise you cannot, or quasi-equilibrium process, otherwise you cannot perform the integration. And if you assume that this fluid behaves as an ideal gas, then U2 remains, U2 will be same as U1, because for ideal gas, if you remember, the enthalpy and entropy changes are functions of temperature only. So for an isothermal process, temperature remains constant. That means internal energy has to remain constant and enthalpy also has to remain constant, because both are functions of temperature only. If that is the case, and if you are applying this conclusion to the first law of thermodynamics, you will find that U2 is equal to U1. So you end up with this equation. That means heat transfer is equal to work transfer, okay, for this process. And if you are assuming the gas to be ideal, you can replace P using this equation. PV is MRT, replace P by MRT by V and perform the integration, so you get this equation, okay. And you can also write the work transfer rate in terms of the pressures, okay. So this is these equations are for the work transfer and heat transfer of an ideal fluid undergoing an isothermal non-flow process, okay. And how do we find the entropy change? Again, you can use the TDS equation, either the first TDS equation or second TDS equation. Since temperature remains constant, you don't have the du or dh terms, so you just have these terms only. That means the second terms of the TDS equations, and if you perform integration, you get these equations. Of course, you can get some conclusions out of this. For example, look at the work transfer equation. If the system is undergoing expansion, that means P1 is greater than P2, then this will be positive, okay. And if it is expanding, system is doing work, so 1W2 is positive, okay. So that is in accordance with our sign change. And if the system is undergoing compression, P1 will be less than P2, that means this will be negative, and 1W2 will be negative. That means you have to supply work to the system, okay. And same similar conclusions for entropy change can be obtained by looking at this equation. For example, if when it is expanding, that means when it is doing work. When it is doing work and if its temperature has to remain constant, that means there must be some heat transfer from the surroundings, only then the temperature can remain constant, okay. That means heat transfer is positive, okay, because work transfer is positive, heat transfer is positive. When heat transfer is positive, you are adding heat to the system, that means its entropy has to change. So that is the case here, because S2 minus S1 has to be positive because entropy is increasing. This holds good here because P1 is greater than P2, so this is positive, this is also positive, okay. Now let us look at another simple process known as an adiabatic process. Generally, adiabatic process means a process in which there is no heat transfer, either to the system or from the system, okay. That such a process is known as an adiabatic process. You can have an adiabatic non-flow process or an adiabatic flow process. Let me give you an example of an adiabatic non-flow process. The example given here is compression and expansion of a gas under perfectly insulated conditions. So you have, let us say, that a piston cylinder arrangement, a gas is contained within the piston cylinder, and you are compressing or expanding the gas, and at the same time all the walls of the system are perfectly insulated, okay. So such a case is an example of an adiabatic process. All adiabatic processes follow the general equation PV to the power of K is constant capital K, okay. And here P is the absolute pressure and V is the volume, and K is known as coefficient of adiabatic compression or adiabatic expansion, okay. And for such a process, the heat and work transfer rates can be conditions. So you have, let us say, that a piston cylinder arrangement, a gas is contained within the piston cylinder, and you are compressing or expanding the gas, and at the same time all the walls of the system are perfectly insulated, okay. So such a case is an example of an adiabatic process. All adiabatic processes follow the general equation PV to the power of K is constant capital K, okay. And here P is the absolute pressure and V is the volume, and K is known as coefficient of adiabatic compression or adiabatic expansion, okay. and for such a process the heat and work transfer rates can be obtained again using the first law of thermodynamic processes for a non-flow situation. Okay, that is this is a general first law of thermodynamic equation. So 1q2 is obviously 0, right, because it's an adiabatic process, so no heat is transferred to the system or from the system. So this is the first law of thermodynamics for an adiabatic process. Okay, and since this term is equal to 0, the work transfer rate must be equal to the change in the internal energy. That is what is shown here. And if you are using this equation along with this equation, you get this expression for work transfer rate. Okay, so that means work transfer during an adiabatic expression is given by K divided by K minus 1 into P2 V2 minus P1 V1, which is nothing but U1 minus U2. Okay, so this is a typical work transfer for an adiabatic process. And if the process happens to be reversible, let us say, that then we have reversible adiabatic process. A reversible adiabatic process is also an isentropic process. How do you prove that? That means a reversible adiabatic process is an isentropic process. That means entropy remains constant. It is very easy to prove this. If the process is reversible, we can use the Clausius inequality that heat transfer rate during a reversible process is nothing but integral TdS. Okay, and since 1q2 is 0 here because it's adiabatic, integral TdS must be 0. Since T cannot be 0, obviously ds has to be 0. That means S1 is equal to S2. That means a reversible adiabatic process is also an isentropic process. Okay, and if the fluid behaves as an ideal gas, then you have an additional relation. This isentropic coefficient K is nothing but isentropic coefficient which is equal to the ratio of Cp by Cv. Okay, and for compressible fluids you can get an additional relation, this additional relation which relates the temperature with pressure ratios and volume ratios. For example, T2 by T1 is related to the pressure ratio by this relation, and it is related to the volume ratio by this relation. These equations are very useful, and we shall see the use of these equations when we perform the actual refrigeration calculations. Okay, now let us look at another process called as a polytropic process. A polytropic process is a general process. A typical example of this process is compression or expansion with heat transfer. That means we have a piston cylinder assembly, and this assembly consists of a fluid, and that fluid is undergoing compression or expansion, and you are not ruling out the possibility of heat transfer. That means during compression and expansion there is some heat transfer between the system and the surroundings, and here the system means the fluid which is undergoing compression or expansion. Such a process is called as a polytropic process, and all the polytropic processes follow a general relation given by Pv to the power of n is constant, where P is again absolute pressure, V is the volume, and n is known as polytropic coefficient, and this n can take values anywhere between minus infinity to plus infinity. That means almost all the processes fall under this polytropic process. For example, where for an isobaric process P is constant. So this is the example of an isobaric process. P is constant, that means n has got to be 0. Okay, so when n becomes 0, P becomes constant, so this polytropic process reduces to an isobaric process. Okay, and when n is equal to 1, Pv is constant, and this becomes an isothermal process, P is constant. Okay, and for an isentropic process the n simply becomes the polytropic coefficient simply becomes adiabatic coefficient, that means F is constant. Okay, and for an isochoric process volume is constant, that means n is equal to minus, sorry, it is not printed here, n is equal to minus infinity. Okay, so depending upon the value of n, the polytropic process encompasses all the processes. Okay, so this is a very general process. Now how do we find the work transfer and heat transfer during a polytropic process? So that is given here. Again I am taking an example of a flow process. Okay, and the work transfer rate here is obtained by integrating integral PdV. Okay, along with the expression PV to the power of n is constant K. Okay, if I am using this these two relations, I can get this equation by integrating PdV. Okay, and this is the general expression for internal energy change. Internal energy change is given by mc into delta T, where phi is the average specific heat at constant volume. Okay, and this is nothing but your a statement of first law of thermodynamics for a non-flow process. What we have done here is 1 Q2 is nothing but U2 minus U1, and this term is nothing but your work transfer rate. Okay, so this is simply your heat transfer in a polytropic process, and the general entropy equation for entropy change in a polytropic process is given by this. This is nothing but the integration of the TDS equation. That means when you perform the integration of the first TDS equation, you get this kind of an expression, and depending upon the relationship between du and T and PdV and T, you can find out what is the entropy change. Okay, for example, if it is let us say an ideal gas, then you can write, and if you are also assuming that Cv is only a function, Cv is constant, then you can write this as Cv dt. Okay, similarly P can be expressed in terms of P by T can be expressed in terms of V. Okay, and you can get expression for S2 minus S1, and this equation is valid for all n except n is equal to 1. So when n is equal to 1, obviously here this becomes you cannot evaluate this. Okay, in such case n is equal to 1, the process becomes isothermal, and as we have seen how to evaluate work transfer for an isothermal process. Okay, and the last process is what is known as a constant enthalpy or isenthalpic process. This is again a very important process as far as refrigeration is concerned, and a typical example of this is the throttling of a fluid. That means a fluid is flowing through a conduit and suddenly it encounters a resistance. Okay, for example, a fluid is flowing through a tube and suddenly a valve is there in the tube and valve is almost closed. So the fluid has to flow through an almost closed valve. That means a large resistance is suddenly imposed on the fluid flow. Okay, obviously what happens, there will be large amount of friction, and because of friction the pressure drops. That means there will be an expansion. Okay, the pressure drops from the inlet pressure to an exit pressure. Okay, so this is an example of a throttling process. Throttling process also takes place when you are forcing the fluid excuse me, through a narrow tube, for example a capillary tube in a Vapour Compression Refrigeration System. Okay. For a typical throttling process, if you are assuming a flow process, that means let us say that we are assuming the process to be steady flow. Okay, and if you are also assuming that the kinetic and potential energy changes are negligible during this process. Okay, then this is nothing but for such kind of a process, if you are assuming that the throttling is taking place in a small area, then there is no area available for heat transfer, so Q dot will be 0, and no work done during this process, so W dot is also 0. So Q dot and W dot are 0 for the throttling process in a steady flow. Okay, and if you are applying the steady flow energy equation which I have discussed in the last class, under these assumptions of negligible kinetic and potential energy changes and no heat and work transfers, you get this equation. Okay, that means finally the throttling process is an isenthalpic process. Doing the fundamentals of heat transfer and fluid flow. Okay, thank you.